Okay, so in this video, we are going to go over some of the scientists that contributed to the atomic theory and then what we know about the atom today. Okay, so we're going to start off with our main homeboy, Dalton. Okay, so Dalton is going to be our first one through this. And what we know about Dalton is he is the father of atomic theory. Okay, so he's the original OG. Okay, father of atomic theory. I don't know why. There we go. My magnification was going there. Okay, so the father of atomic theory. So he was the first one to come through and kind of come up with these 5 postulates. Okay, so he is known for his 5 postulates. So our first postulate. Okay, he stated that all elements are made up of atoms and it is impossible to divide or destroy those atoms. So kind of bear with my handwriting here. Okay, so his first postulate, all elements are made up of atoms and it is impossible to divide or destroy those atoms. Okay, so what I want you to do is you would put a big star by this one because that has since been disproven. Okay, so we know that we can actually break down atoms even further. Okay, so things like decay or other instances. So we can break it down further. So this postulate has been disproven. Okay, so it's still impressive they did it at that time, but the first postulate has been disproven. Okay, so postulate number 2. Okay, all atoms of the same element are alike. Okay, so what I'm going to do is I'm going to go ahead and put another red star by this one because this one has been disproven as well. Okay, not all atoms of an element are alike. Okay, so we've briefly talked about things called isotopes. Okay, so these are varying versions of elements. Okay, so we can have things like carbon 12, carbon 13. Okay, so they're both carbons, but they are different. And what's different about them is the actual number of neutrons present there. So it can still be carbon because they still have those 6 protons, but they have varying numbers of neutrons, so that makes them isotopes of each other. Okay, so this second postulate has been disproven. Okay, so let's move on to our third postulate. Third postulate, atoms of different elements are different. Okay, this makes sense. This is true. Okay, so I'm not going to compare carbon to oxygen. Okay, so atoms of different elements are different. Okay, our fourth postulate, atoms of different elements, okay, can combine. Ooh, that was just bad handwriting right there. Can combine to form compounds. Okay, so that makes sense. So it means we can have differing elements come together and make something as a compound. So an example of that would be something like H2O. So hydrogen and oxygen come together and make water. Okay, so our last postulate, okay, in a chemical reaction, atoms are separated combined or rearranged. Okay, so that is something we'll go over more in that towards the end of this semester, is when we actually start doing chemical reactions where you take two different compounds and you start mixing, okay, and we can create something different. Okay, so these are our 5 postulates. So Dalton, when he was looking at the atom, he thought of it, and I'm going to put this in a different color. Okay, he thought of it as the billiard ball model. Okay, so he thought the atom was just a perfect sphere, and this should get real interesting. Is me trying to draw a perfect sphere. I'm just gonna do a little circle like that. Okay, so he thought the billiard ball model. So this was the atom, was just a billiard ball, nothing to it, just a nice sphere. Okay, so still not bad for during that time. So you got to think this was back in like 1800 when he was doing this. Okay, so he just thought it was a nice sphere. Okay, so that is it for Dalton. So now what we're going to do is we're going to go on to J.J. Thompson. Okay, so I'm going to screw it down here a little bit. So now we have, let me change up my size. It's a little too big. Okay, let me erase that real quick. Okay, so we have J.J. Thompson. Okay, so what J.J. Thompson came and did, it was he used the cathode ray. Okay, so basically what the cathode ray was is he was firing particles. So he was firing charged particles from one end to the other. And when he added a magnet to it that had a positive into it, the particles actually attracted to it. So that meant there was something negative there being attracted to that positive. Okay, so the big takeaway from J.J. Thompson is that he discovered the electron. Okay, so electrons are charged with a negative charge. Okay, so when he added a positive charge anywhere near it, these electrons would be attracted to it. Okay, so he knew that there was something negative. There's a negative charge inside that atom. Okay, so what his model looked like is, now I'm going to do a different color. Okay, so JJ's model, and let me go back to a different size. So JJ's model is called the plum pudding model. Okay, so bear with me on this. So let's see. His was the plum pudding model. Okay, and that is some weird English thing that they eat. Okay, plum pudding is just basically pudding with raisins in it. Okay, so what he discovered is, let me choose a different color here, is that there were negative charges located throughout this atom. Okay, so there was negative electrons in there, and then the atom itself was actually positive. Okay, so this whole blob was positive, and it just had negative charges dispersed throughout it. Okay, so that was why it was called the plum pudding model. Okay, so that was J.J. Thompson. So now we move on. So now we are going to go to Rutherford. And let me make sure I'm in the right color. So now we're in Rutherford. Okay, so what Rutherford did is he had the gold foil experiment. So the gold foil experiment. So that is his main experiment to discover. Let me change up color again. So he discovered the proton. I'm sorry. He discovered the protons, but he discovered that there was a positive charge in the center. Okay, so he'd actually found out there was a small, dense, positive nucleus, where protons are. So let me fix that real quick. So he discovered there was a small, dense, and positive nucleus. Okay, and so the way he did that is he was firing these positively charged particles through gold foil, and he realized that most of them were going through, but there were some that were actually bouncing back. Okay, so what happens when we hit a positive with a positive? They repel each other, so they're going to bounce back. So they're going to go away from each other. So let's see if I can get an attempt for me to draw this. His model. Okay, give me 1 second, just playing with this. So what he discovered was there was this positive, small, dense, and positive nucleus. Okay, and then get some different colors and a different size. Sorry, this is not very easy to go back and forth on. Okay, so we had this positive center of the nucleus, and then we had negatives just kind of floating around. Okay, so he discovered there was a lot of empty space, okay, around that nucleus. Okay, so it just wasn't a billiard ball. It wasn't a blob of positive with negative speckled through it, like Thompson said. Rutherford found out there was a positive center, and it had a lot of space with negatives floating around it. Okay, so we had a positive center. So this whole nucleus was positive. Okay, so our next scientist. Okay, so I usually refer to Bohr. As I've heard so much about this, I'm getting bored now. So Bohr. Now what he did is he went a little bit further. Okay, so Rutherford discovered there was electrons floating around this small nucleus, and he just thought that they were just kind of there. So what Bohr did is, I'm going to attempt to draw this now. So I'm going to try to use the same colors as Rutherford's. Okay, so we still have this dense, positive, small nucleus in the center. So let me change up my size. So we're still a positive nucleus. Now let's change my colors. And what he did is, instead of these electrons just randomly floating, he discovered that they were sitting on certain energy levels. Okay, so instead of just floating around, they were on these specific energy levels. And let me get a different color. So I had electrons floating on these levels. Okay, so they're found on these specific energy levels that are they're at a fixed distance from the nucleus. Okay, so we cannot change these energy levels. We cannot change the distance from the nucleus. So they are stuck where they're at. And then there's still space in between those levels where nothing resides. So these electrons are specifically on those levels. So this is what Bohr did. He took a little bit further and discovered that there were certain energy levels where these electrons resided. Then our last experiment, to sum this up, is we had the quantum mechanical model. So the quantum mechanical model took it even further. So we still have our dense positive nucleus. Okay, so we still have our dense positive nucleus. Getting a little bit faster at this. Nope, just messed it up. Okay, so dense positive nucleus. Now let me change the size of this. Okay. Now Bohr, his made it look nice and neat because it was all nice and flat and everything looked neat. Okay, but the quantum mechanical model states that these electrons are actually found in orbitals. So these are actually like 3D orbitals. So it's not just a flat disk. So now I'm going to attempt to draw that. Okay, so we still have these energy levels, but they can exist on these different planes. Okay, so they can exist on three-dimensional planes, so they can be going forward, backwards, side to side. Okay, so it made it more of a three-dimensional feel. So the quantum mechanical model came through and improved it even further, basically stating that they are on orbitals that can go any direction and that they are located in the electron cloud. So they discovered that these electrons were found in the electron cloud. And that's it.